Astrophysicists have, they easily have the biggest telescopes and the most advanced math in human history,
Oh,
right?
without a doubt.
They map out galaxies billions of light years away. They predict where black holes are going to be. So what happens when those exact same scientists suddenly realize they are just, fundamentally wrong about how the universe actually works?
Oh, you basically end up with a highly productive panic in the scientific community.
And productive panic, I like that.
Yeah, it forces us to question the very foundation of how we measure reality itself.
And that is exactly what we are exploring in today's deep dive. We are jumping into a May 14th, 2026 article, and it details this landmark study that just hit the community back on April 10th. It was published in the journal Astronomy and Astrophysics.
Right.
Our mission today is to really understand this phenomenon that everyone's calling the Hubble tension. It's this growing scientific crisis revealing that the universe is expanding, well, way faster than our meticulously crafted models predict.
It really is a crisis, yeah.
So we get a front row seat to watch the smartest minds on Earth realize they have to essentially rewrite the rule book. But, okay, let's unpack this. Before we can understand why physics is quote-unquote breaking, we have to understand how we even measure the universe in the first place, right?
Exactly. To wrap your head around the Hubble tension, you really have to look at the core conflict. And that conflict basically comes down to two very different ways researchers determine the expansion rate of the universe.
Okay, so what's the first way?
Let's start with what we can call the local method. So this approach focuses on objects that are, relatively close to us in the grand scheme of the cosmos.
Close being a relative term here, obviously.
Right, exactly. So researchers measure our distance to specific stars and nearby galaxies. And by calculating how fast these measurable objects are moving away from us, they basically lock in the expansion rate.
And this local method, it consistently indicates that the universe is expanding at around 73 kilometers per second per megaparsec. And I actually want to pause there for a second because we hear that unit all the time in cosmology.
Oh, sure. 73 kilometers per second per megaparsec. It's a mouthful.
It really is. For someone trying to visualize space stretching out, what does that number actually look like?
Well, a megaparsec is a unit of distance. It's equal to about 3.26 million light years.
Okay.
So imagine a giant cube of space that is 3.26 million light years wide. What that number means is that for every single megaparsec you look out into the universe,
Well,
a galaxy appears to be receding from us 73 kilometers per second faster.
wait, let me make sure I have this. So if a galaxy is 1 megaparsec away, space is stretching, so it moves away at 73 kilometers a second.
Yep.
And if it is 2 megaparsecs away, it's receding at 146 kilometers a second.
You've got it. The further out you look, the faster the actual fabric of space itself is stretching between us and that object.
So it's this huge compounding effect. Okay, I get it. But then we have the second method, the early universe method, right?
Right. So instead of looking at what is happening close to home right now, this second method looks way back to the primordial radiation left over from the Big Bang.
The cosmic microwave background.
Exactly. Scientists take that ancient data, those microscopic temperature fluctuations from the very early universe, and they run it through the standard model of cosmology.
Which is like our master mathematical rule book.
That's a great way to put it. That model accounts for all the normal matter, the dark energy we think is out there, and it basically calculates what the expansion rate should be today, purely based on how the universe started.
But the estimations based on that early universe data give us a significantly slower value than the 73 we just measured locally.
Right, usually around 67. And this raises a really important question. How can a physical measurement of the universe today completely disagree with the definitive mathematical predictions based on the universe's origin?
Okay, let's try to ground this for a second. It's almost like trying to figure out how fast a car is moving down the highway.
Okay, I like where this is going.
So the early universe method is like sitting in a mechanic's garage, right? You're studying the car's original engine specs and the blueprints straight from the factory. You are calculating its theoretical top speed based strictly on those foundational documents.
Yeah, and taking that car analogy a step further, the local method isn't like a radar gun directly measuring the speed from the outside.
Right.
It's more like you are sitting inside that very same car, looking out the passenger window, and actually clocking the physical mile markers zooming by on the highway to calculate your speed in real time.
So the crisis here is that the physical mile markers out the window show we are moving way faster than the original engine specs say is even physically possible.
Exactly.
And when you face a contradiction that massive, I mean, you really only have two choices. Either your factory blueprint is fundamentally flawed, or your passengers are just reading the mile markers wrong.
Which means if you were going to go out there and claim the blueprint of the universe is broken, you better be absolutely 100% certain you are reading those mile markers correctly.
Right. Which brings us directly to the new April 10 study. This paper is, it's entirely about confirming those local mile markers with a level of precision that just eliminates any lingering doubt.
Precisely.
And in the source material for this deep dive, there's this really incredible artistic image. It's designed to help us visualize how astronomers actually measure these massive distances. It shows this glowing, twisting ladder kind of floating and extending out through a vast, dark web of stars and galaxies.
Oh yeah, it literally looks like a staircase made of light stretching into the void.
Yeah.
That represents what we call the cosmic distance ladder.
Right, because we can't exactly stretch a tape measure across the
Right.
galaxy.
Obviously not. So we have to use a succession of overlapping methods to measure distances. Every single rung of that ladder provides the specific mathematical and observational data you need to determine the distance to the next rung.
Okay.
So you measure something relatively close to calibrate your tools for something a little further away, and then you use that to calibrate the next measurement, basically stepping your way out into the deep cosmos.
See, I have to push back here for a second, because this has always seemed like a massive vulnerability to me.
How so?
Well, if you are building this ladder and you use, say, a specific pulsing star to figure out the distance to the next galaxy, I mean, isn't relying on one type of star incredibly risky?
Oh, absolutely.
Like, what if our understanding of that star's behavior is just slightly off? Maybe because of cosmic dust or some strange chemical composition we didn't account for.
Yeah.
If the first rung is even slightly warped, the error just multiplies as you climb, the whole ladder collapses.
What's fascinating here is, well, the researchers behind this new study completely share that exact concern.
Really?
Yeah, that exact vulnerability is what astronomers have agonized over for decades. A single linear ladder with single points of failure, it just was no longer sufficient to challenge the standard model of the universe.
But what did they do?
They re-engineered the entire concept of cosmic measurement. This new effort was led by a collaboration called the H0 Distance Network, or H0DN. Instead of relying on a single technique to build a linear ladder, they combined decades of separate observations into an interconnected network.
So it's not a single ladder anymore. It's more of a woven web of different measurements. You aren't just trusting one fragile rung.
Exactly. To ensure absolute precision, this network links multiple independent measurement methods and cross-checks them against each other. Let's look at the mechanics of it. First, they use Cepheid variable stars.
And these are the stars that pulse, right? Like they expand and contract over a period of days or weeks.
Right, and more importantly, their pulsation rate is directly tied to their true intrinsic brightness. The slower they pulse, the brighter they actually are.
Oh, wow.
So because we know their true wattage based on their pulse, we can look at how dim they appear to us on Earth and calculate exactly how far away they must be.
That makes sense.
But to avoid the exact trap you mentioned earlier, relying entirely on Cepheids, the network layered in an entirely separate method. They use red giant stars.
Yeah, the text mentions using the luminosity of red giants. How does that work?
Specifically, they look at something called the tip of the red giant branch. So when certain stars reach the very end of their lives, their cores hit a critical temperature and they undergo a helium flash.
Okay.
Right before that flash happens, every star of a certain mass reaches the exact same peak brightness. It is an incredibly consistent cosmic standard candle.
So you have the Cepheids pulsating over here, giving you one distance measurement, and then you have these red giants reaching their helium flash peak, giving you a completely different way to measure the exact same distance.
Yes. And the network doesn't stop there. It also incorporates Type Ia supernovae, which are exploding stars that reach a very specific known mass limit before detonating with a consistent brightness.
Wow.
And they even use the rotation rates of entire galaxies.
Okay. If we bring this back to our car analogy, it's not just one person looking out the window anymore.
Not at all.
It's like having 5 different passengers in the car, and each one is using a completely different map application, tracking completely different landmarks, and they all suddenly agree, down to the decimal point, on the exact mile marker we just passed.
That's exactly it. If the Cepheid calculation says a galaxy is 50 million light years away, And the red giant calculation for that same galaxy also says 50 million.
And the supernova that went off in that galaxy also calculates to 50 million.
Right. You've effectively eliminated your blind spots. That overlapping calibration is the very core of the HDR distance network.
So they're verifying the results in multiple, entirely independent ways.
Yes, practically eliminating the risk of systemic error from any single method.
Which leads us to the grand reveal of this deep dive. By intertwining all of these methods, by weaving decades of independent data into this massive network, the researchers locked in their final number on April 10th.
And the resulting measurement for the local expansion rate is 73.50 plus or minus 0.81 kilometers per second per megaparsec.
73.50, and that plus or minus 0.81. I mean, that means they have narrowed down the expansion rate of the universe to an unprecedented precision of just over 1%.
It's unbelievable. In astronomical terms, where we used to be happy just getting the general order of magnitude right, a 1% precision is staggering.
Yeah, that's wild.
It is officially the most precise direct measurement of the local expansion rate ever recorded. And closing that error margin to 1%, it formally closes the door on statistical flukes.
So there's no more blaming the tool.
Exactly. It's the transition from, maybe our telescopes are miscalibrated to our fundamental physics is broken.
Because if the local measurement is 73.50 and it is undeniably accurate, the tension just got a whole lot worse. The blame for this massive discrepancy shifts entirely to the other side of the equation.
It's just right to the early universe blueprint. As we discussed, the slower predicted rate of around 67 relies entirely on the standard model of cosmology.
Right.
This model is our definitive mathematical description of how the universe evolves. It accounts for the cooling of the plasma after the Big Bang, the distribution of galaxies, the background radiation, all of it.
And here's where it gets really interesting. If the standard model prediction for the current expansion rate is this definitively wrong, then the rulebook is just incomplete. So what does this all mean? I want to make sure you, the listener, really grasp the sheer scale of the implication here.
It's massive.
It's not a simple math error. It means the actual stuff the universe is made of, or the fundamental forces governing it, are operating under rules we just do not possess. It's like we baked the cosmic cake, but we left something out of the recipe, and now the cake is rising way too fast.
That's a perfect analogy. And the source material highlights 3 distinct possibilities for what that might be. 3 potential missing ingredients that could be throwing off the standard model's predictions.
Okay, so if the mile markers are undeniably correct, the factory blueprint is missing parts. What's the first possibility? What happens if the dark energy we put into the blueprint isn't just a static background hum?
That is the first major possibility right there. We might not fully understand the behavior of dark energy.
Dark energy being the mysterious force accelerating the expansion of the universe, right?
Right. In the current standard model, we treat dark energy as a cosmological constant. We basically assume its density remains perfectly uniform over billions of years.
But if the universe is expanding at 73.50 locally, well above the prediction,
Then dark energy might not be constant at all. It could be dynamic.
Yeah.
We call this quintessence, which is a theoretical field that actually changes over time.
oh, wow.
Yeah, so if dark energy was weaker in the early universe, which allowed structures to form, but has grown significantly stronger or denser in the billions of years since, well, our models based on the early cosmic microwave background would fundamentally underpredict the expansion rate we see today.
Okay, so that's dynamic dark energy. But if it's not dark energy acting up, maybe the actual materials inside the cosmic factory were different? Like, what if there are completely unknown particles floating around out there in the dark that we haven't discovered yet?
That's the second idea. The early universe was this dense, incredibly hot soup of interacting particles. And the standard model very carefully accounts for the particles we know about: photons, electrons, standard neutrinos.
Sure.
Their interactions dictated how radiation and matter basically pushed against each other. But if we introduce dark radiation, perhaps a completely unknown extra species of neutrino, it totally changes the physics of that soup.
How does an extra invisible neutrino actually break the math, though?
Well, an extra particle species would have added additional energy density and radiation pressure to the early universe.
Okay.
That extra pressure would actually force the universe to expand significantly faster before the cosmic microwave background radiation was even emitted.
Which means the foundational starting line we use to calculate everything else is shifted.
Precisely. It alters the size of the sound waves traveling through that early plasma. And since we use the size of those ancient sound waves as our baseline cosmic ruler to measure the early universe, shifting that baseline totally invalidates the math that gives us the slower expansion rate.
Just invisible, unknown puzzle pieces shifting the entire board before the game even started.
Exactly.
So we have dynamic dark energy, and we have these phantom particles. What is the third possibility?
The third possibility is, well, perhaps the most profound. Our understanding of gravity itself might require modifications.
Wait, you mean Einstein's general relativity?
Yep.
But it has passed every test we've ever thrown at it, from predicting black holes to gravitational waves?
It absolutely has. But it has passed every test on the scales of solar systems and individual galaxies. When you attempt to apply general relativity to the absolute grandest scale of the entire expanding cosmos over billions of years,
It might be incomplete.
it might be. We might be seeing the very limits of Einstein's equations. There could be modifications to how gravity behaves over immense cosmic distances. It could be weakening faster than predicted, for example.
Wow.
Yeah, if gravity operates differently on a macro scale, the standard model, which relies entirely on general relativity, is built on a faulty foundation.
Dark energy behaving dynamically, an undiscovered species of particle altering the early radiation, or the fundamental rules of gravity just shifting under our feet. I mean, any one of those would require entirely rewriting the science textbooks.
If we connect this to the bigger picture, this is exactly why the Hubble tension is so thrilling. It is very easy to look at a broken model and view it as a failure of modern science.
Right, like, oh, we got it wrong.
But it's the exact opposite. This tension, this definitive 1% precision proof that our blueprint doesn't match the reality, it means we are standing on the precipice of a brand new era in physics.
It's like a giant flashing neon sign pointing toward a deeper truth we just haven't uncovered yet. The H0 distance network, they didn't just calculate a highly precise number, they practically measured the exact dimensions of the gap in human knowledge.
Exactly. They isolated the anomaly. The universe is telling us that reality is richer and just more complex than our current equations can handle.
Let's take a second to look back at the journey we've taken today. We started with the Hubble tension, this epic tug of war between the early universe blueprints and the real-time local measurements. You now understand how the H0 distance network upgraded our fragile distance ladder into an interlocking, ultra-precise web.
Yep.
By calibrating the pulses of Cepheid variables against the helium flashes of red giants and the explosions of Type Ia supernovae, astronomers eliminated their blind spots.
And through that calibration, you can understand why the resulting expansion rate of 73.50 kilometers per second per megaparsec is officially breaking the standard model of cosmology.
The real takeaway here, the reason this matters, even if you never look through a telescope in your life, is what it says about the nature of facts. Even the most foundational models built by the greatest scientific minds, they are always subject to revision when new, better data arrives. It is a powerful reminder to just maintain a mindset of lifelong curiosity, to constantly refine your own blueprints when the mile markers out the window don't line up.
Science is just a rigorous process of getting progressively less wrong. And this study is a monumental leap forward in that exact process.
Before we wrap up this deep dive, I want to leave you with one final lingering thought to mull over, something to take with you into your day.
Okay.
We just explored how our foundational models are clearly missing massive elements, whether that is dynamic dark energy changing over time, completely unknown phantom particles, or a modified version of gravity that operates differently on cosmic scales. We need these missing pieces just to explain why the universe is stretching out so fast. So you have to ask yourself, if the fundamental laws of physics themselves aren't static, if the invisible rules governing the entire universe are actively evolving and changing as the cosmos expands, what else about our everyday reality is quietly shifting around us right now entirely without us even noticing?